Hello physics students. In the last physics video, we learned about something called a capacitor. A capacitor is any two chunks of metal, one here, and what you do is you take a certain number of electrons off of atoms. So let's suppose I have 10 atoms on this side, from which I strip one electron off of each of those atoms and then I deposit them on this side. So this basically has now 10 protons without a partnered electron. And here we have 10 extra electrons. So we say this capacitor is charged even though these two plates, the total charge is 0 because we have plus 10, negative 10. So really a capacitor is always neutral even when we consider it charged. But now what happens is these electrons over here are attracted to the 10 protons over here. They would like to jump the gap between, but they can't. So what I do is I connect the wire from one metal to the other, and then when the electrons run through that wire, to get to these protons, they can go through like a light bulb or some electric motor or something. So what I've done is I've stored a bit of energy. We say we store charge in a capacitor and we store energy in a capacitor. So that's what we learned yesterday. Today what we're going to do in this video is learn what happens when you connect multiple of those capacitors together, either in different patterns. One pattern is called capacitors connected in parallel, and the other pattern is called capacitors in series. So we're going to begin today with what we call parallel capacitors. So notice I have a voltage source here. This is like a battery, and the schematic of a battery is 4 lines, one large, small, large, small. This means a battery, and the large line is like considered the positive terminal of the battery, and the small, the negative terminal of the battery. So what happens is electrons come out of the negative terminal here and they get drawn into the positive because of chemical reactions. Different than a capacitor where you have products and reactants and then that pulls electrons from one molecule to the other. So that's what's happening here. Electrons are going to come out of this end and then they're going to be deposited on these 3 capacitors. So this is considered a parallel arrangement because these are connected to the battery in such a way that all the plates on one side are connected through wires directly to a battery, and all the wires on the other sides of the capacitors are connected directly to the battery without anything in between. That's the key of a parallel circuit of capacitors. The other thing I want to point out is again a reminder that voltage is always from one point to another. So like a battery has to have one prong and another. So this is the voltage, say it's a 9-volt battery, 9 volts between these 2 terminals of the battery. Another thing, just a little minor point, we dropped the delta V in circuits. Voltage is normally in electrostatics, it's considered V when you compare it to infinity. When you compare it from one point to another, usually there's a delta here. But in circuits, as I said, we just call it V just for convenience. But we're really talking about delta V here. So what is true in this case? Because each of these capacitors is connected directly to both terminals of the battery without anything in between, each capacitor gets the full voltage of the battery. In other words, if the battery is 9 volts, then 9 volts, 9 volts, 9 volts to all 3 of the capacitors in parallel. Now, the charge, though, gets split up. So imagine this battery sends out 10 electrons. We might have 5 that go here, 4 that go here, and 1 that goes here. So they kind of split up. That's what this formula is saying. You can't have an electron that goes to both capacitors. It's going to, or all 3. It's got to choose one of them. And then what happens is, of course, when we charge this with, say, 2 electrons, then that means 2 electrons have to come out of this side. That's how a capacitor works, leaving this side with a deficit of 2 electrons. In other words, 2 protons that are unpartnered. So we might have, like I said, let's suppose 2 here, maybe 3 here and 5 here. That's a total of 10 electrons that went through the battery. So this is how we state that mathematically. They add up to the total. Now, because when you hook more capacitors to a battery instead of one, if this stores 2 electrons and this 5 and this 3 or something, then we have more total charge in the entire circuit for the same voltage battery. And if you're storing more charge for the same volts from this basic equation, more charge for the same volts means the capacitance of this whole system goes up. And so what we then can calculate is like the total capacitance of the entire arrangement, and we call that the equivalent capacitance. CEQ stands for the equivalent, or like what the net effect is of all of the capacitors together, and you just add up to get the total capacitance. So more capacitors in parallel, you get more capacitance, more ability to store charge. Kind of makes sense for parallel. Now, if instead we connect the capacitors in a chain, let me pause to allow you to catch up if you need a moment to catch up with these notes. Okay, so these in parallel, you can also connect capacitors in a chain. Notice what happens here. Instead of them being like this, one after another, like a sequential arrangement. What happens here now is that the full volts of the battery does not go to any one particular capacitor. Remember, voltage is 2 prongs. Every wire has 2 prongs. So this is one side of the 9-volt battery. Here's the other side of the 9-volt battery. So it applies across all of them. And so the voltage here, if you do electric field times distance, as you're integrating along, you have to add the ED here, electric field times distance, add electric field times distance. So in other words, the voltage gets split up. We write that mathematically here. Like for example, if we put 9 volts here, we might have 3 volts, 3 volts, 3 volts, or an unequal sharing, like maybe 5, 2, and 2. But the point is the battery voltage gets split up among the capacitors. However, any electron that comes out of here, let's suppose 2 electrons come out of this side of the battery and they deposit themselves on this plate of the capacitor. Then as we learned, 2 electrons have to come off this side and move out of this end. So they're going to now go here and deposit. And how do you charge one side of the capacitor negative? You've got to charge the other one positive. So 2 electrons would come here, 2 would come off. And where do these 2 go? They go to this side. And then 2 come off, leaving this side positive. Notice whatever charge I put on this plate is what all capacitors will have. So in other words, mathematically, the total charge coming out of the battery is whatever is on each of the capacitors. Now, what happens in this case is because you're splitting up the voltage, each capacitor will store less charge than if it were alone on the battery. And that means the arrangement of capacitors stores less charge. Kind of counterintuitive that you would put more capacitors into a circuit and the capacitance goes down because the voltage gets split in series. So the way you can calculate, I forgot something. The way you can calculate the equivalent capacitance of this arrangement is you sum up the reciprocals of the capacitances and then you take the reciprocal of the answer. And some people might look at this formula and say, well, why don't you just do C1 plus C2 plus C3? If you're doing the reciprocals and then you take the reciprocal, don't you just get the original C1 plus C2 plus C3? Not true. Try it with, let's suppose we got 3 capacitors that are 3 farads each. Try this, 1/3 plus 1/3 plus 1/3 to the negative 1 power is 3 over 3. Flipped over is still 3 over 3, or 1 is the capacitance. Is that the same as 3 plus 3 plus 3? No, it is not. That gives you 9. So yes, you have to keep the reciprocals in the sum and then take the reciprocal of the answer. Okay, so this is 2 ways to connect capacitors. Let me pause and give you a chance to catch up if you need it. Okay, so now what I'm going to do is I'm going to do a couple quick calculation examples to show you how you can use these formulas and these concepts to figure out different things about circuits connected in series or parallel. So let's begin with example 1. All right, so we have two capacitors, C1 and C2. Given those values, those capacitances, we connect them in parallel to a 12-volt battery. So basically what we have is a 12-volt battery like this. So this is 4 microfarads and 6 microfarads and 12 volts here. So the first thing for the equivalent resistance, maybe I'll label that A. What you want to do is you want to use that the simple rule when in parallel, the capacitances add. So the total capacitance of these two will just be C1 plus C2. In other words, 4 microfarads plus 6 microfarads equals 10 microfarads. You're welcome to leave the micro unit throughout and just carry it through and leave it that way. The next thing, the total charge. In order to find the total charge, you use C equals Q over V. But what you do is now you use to find the total charge, you're going to use the total capacitance over the total volts. Total capacitance, total volts gives you total charge. Multiply the 12 to the other side, and basically you get, maybe I'll do it right here. (120 microcoulombs). So there's the, and by the way, as you see, I left the micro there. I could put 10 times 10 to the minus 6 here and get 120 times 10 minus 6 there and leave the answer in coulombs, or I could just carry the micro unit throughout, and that's also acceptable. Another way I could have done this is I could have found the charge on each of these using C equals Q over V for this and that, giving me a Q here of 48 microcoulombs. And then do the same thing, C equals Q over V, 6 microfarads equals Q over 12. Multiply the 12 to the other side, and I get 72 microcoulombs on this one. And then add them up and get 120. So my point is that a lot of times in these circuit problems, you can use many different ways to solve the answer and get a correct result. All right, let's move on to the next example. All right, if you need a moment to catch up, then I'll create a pause here to allow you to copy the rest of this down. Okay, so example 2. Okay, so we have the same two capacitors, the same battery, but this time we're going to connect them in series. And then we're going to calculate all those various results. So again, this circuit will look like this. Now, by the way, some people might say, that doesn't look like the diagram you drew before. It doesn't look like series. It is because they're in a chain. So they don't have to be looking the same as the diagram I erased over here when I had the notes. You have to just think more schematically if the circuit behaves a certain way. Like, for example, instead of putting the 6 here, I could have put it down here. And that would have thrown some people off. They would say, oh, those are in parallel. No, they're not. They're in a chain, right? So whatever electrons come out here, they deposit, then they come off, they deposit, then they go back to the battery. So that is schematically a series circuit. So you got to think more that way than the shape of what it looks like. Okay, so the first thing, the equivalent capacitance. So that's the reciprocal rule. So I plug in the numbers for the capacitances. Again, I could leave the micro unit and my answer will just be in micro. I'm going to leave a little space over here for a common denominator and a little space over here. Now, you could just punch this on a calculator, 1 over 4 plus 1 over 6 parentheses to the -1 power, and you'll get the correct answer. Or you could do common denominators. Like this can be thought of as 3 over 12. And this as 2 over 12. So when I add those up, I get 5 over 12. Flip that over, it gives me 12 over 5. And then that comes out to be 2.4 microfarads. Okay, so that is the result there. Okay, the next thing, what I want to do is find the total charge. So once again, I can use C equals Q over V as long as I use the total capacitance and the total voltage. I'll get the total charge. The total capacitance is 2.4 microfarads. The total charge is what I'm looking for. And the total volts is 12. So if I multiply the 12 to the other side, I get, I believe it's 28.8 microcoulombs. Okay. Next thing, I want to determine the voltage that this capacitor has on it. Remember, in series, they don't get the full 12. They split it up. Maybe it's 6 volts and 6 volts. Maybe it's 2 volts and 10. Some kind of split of 12 from one to the other. How do you find that? Well, what you could do is, that's part C, is the voltage for the 6 is I could use C equals Q over V, because if I use the capacitance of the 6 microfarad, and I know the charge on the 6 microfarad. How do I know that? You say, I only know the charge that's in the whole assembly. Remember, in series, whatever number of electrons come out here, they also go to here and around. So 28.8 microcoulombs came out of the battery. It went here. 28.8 went here also. So that's the charge, 28.8. And I'm looking for the voltage on the 6 microfarad. So I move this over, I get 6V equals 28.8, divide 28.8 by 6, and I get the delta V. See, I'm kind of throwing the delta in there and sometimes leaving it off. It's fine either way. So that's going to give me 4.8 volts. Okay. Actually, maybe I'll do it here like this. And part D, to find the volts in the 4 ohm, I could repeat this process. C equals Q over V. If I use the capacitance of the 4, which is 4 microfarads, and the charge, again, 28.8 came out, 28.8 here, 28.8 here. So I do 28.8 microcoulombs. And what's the delta V on the 4 microfarad? So I multiply the V times 4, so I have 4V equals 28.8, divide 28.8 by 4, and I get my delta V is, what's that? No, 7.2 volts, okay? So there it is, okay? So let me create a pause, give you a chance to catch up if you need it. Okay, one other thing I want to point out before I go on to the next thing is that I found, so I know that this is 12 volts right here, and then I found that this one was 4.8 volts. I could have found this one by subtracting, because notice that these two add to this. So this is clearly the difference of 7.2. And again, you're welcome to do it that way. Set up an equation, V equals V1 plus V2, and then plug in and solve. There are multiple ways to solve these circuit problems. Okay, so those were the simple kinds of circuits you could create. Either everything is in series or everything is in parallel. Well, in a real device, you can have a more complicated kind of circuit. You could have some parts that are in series, some parts that are in parallel to do whatever you need the device to do. So that's what we're going to look at now, a circuit that's a combination of series and parallel in different places, and see how we could analyze that to figure out voltage and charge anywhere in the circuit. So let me sketch an example. We'll, let's see, pick some numbers. So combination. I call these combination circuits. Okay, so okay, so here's my circuit. I have a 4 microfarad, then two 8 microfarads, and a 2 microfarad over here. So what we're going to want to do, the equivalent capacitance of everything, All right, so there is the problem. So what we want to do is find, again, the equivalent capacitance of everything together. The voltage right here, it's not going to be 12, it's going to be some portion of 12. And then the charge in this and the voltage in this capacitor. So how do we do that? What we have to do is begin by looking at the circuit and trying to see a place where the circuit is either pure series or pure parallel. Okay, so for example, we do not start here by saying this is in series with this because the electricity goes like this. It's not truly in series because in order for these two to be in series, all the charge that came out of this capacitor must then deposit over here. But you can see that there's a break here. So let's suppose 10 coulombs comes out of here. Maybe 2 of it goes here and 8 there. So this has 8 and this has 10. They don't have the same charge. They're not truly in series. You might be saying this 8 and this 2 are in parallel because they look like, parallel. Also not true. Because in order for things to be truly in parallel, the two positive sides have to be connected with only wires, and then the two negative sides are not connected with wires. There's this in the way. So these are not truly in parallel. They don't share the same voltage. The place we must start to simplify this circuit is right here. This portion of the diagram is definitely in series. Okay, so that's where I begin. And so I can find, first of all, this is part A, I can find the equivalent capacitance of these two by doing 1/8 microfarads. And I'm skipping writing the equation out because I don't know if I'm going to fit all of this whole calculation on this board, and I would like to because otherwise it will get too confusing. So right here, this is going to turn out to be 1/8 plus 1/8 is 2/8. Flip that over is 8/2 or 4 microfarads. So these two capacitors together act as one. That's 4 microfarads. In other words, I could pull them out and put a 4 there and the battery would not know the difference. It would feel the same way and the circuit would perform the same way to the battery. So what I'm going to do now is resketch this entire circuit. Okay. Yeah, actually, you know what? Let me create a pause here to give you a chance to copy this because I'm going to erase a little bit of it. Okay, so let's continue on. And I'll remember that this is the 2 microfarad here. And I'm going to kind of try and scrunch this up. Maybe I'll get 3 segments over here to fit everything in. So I redraw the circuit as I said. So here is the battery. The 4 is still here. And then the 2 microfarad is still here. But in this middle branch, we have just figured out that these two can act as one 4 microfarad capacitor. Now, I look again to simplify. I look for a part of the circuit that's either pure series or pure parallel. For the same reason, this and this are not in series, same as before over here. But also these and these are not in series. Because again, some of the charge here splits, so these two don't have the same charge. The part of the circuit that is definitely in series or in parallel is right here. These two are both definitely in parallel. Okay, so let's try and be a little tighter here. Definitely in parallel. And the rule for adding parallel capacitors is you simply add them. For 6 microfarads. Okay, so these two, again, to the battery feel like one 6 microfarad capacitor. So I can redraw the circuit and replace these two with a 6 microfarad capacitor. And our 12 volts is still here and here. So now this is really quite simplified because now those are definitely in series. So I can use the series rule once again to find the equivalent capacitance. And you could do common denominator, or you could punch it on your calculator, or you could remember from the last, it was basically this one of the series example. This is 2.4 microfarad, the equivalent capacitance of all the capacitors together. So that's what you do. Look for series, simplify, replace. Parallel, simplify, replace. Okay? And then and you keep, the more complicated, the more steps it takes to eventually get it down to one capacitor. So to the battery, all of these feel like one capacitor that's 2.4 microfarads. Replace all these with one capacitor, the battery would not know the difference. Okay, so that's part A. Part B, what's the voltage right here? Okay, so what we would do is we would first have to find the charge that comes out of this arrangement. So we could do that with C equals Q over V. And to try and conserve space, I'm going to cram this in over here and say that we've got a 2.4 microfarad capacitor. What's the charge for 12 volts? And as we saw that before, same numbers, but basically you multiply 12 to the other side, and you get 28.8 microcoulombs. Now that's not what they wanted. They wanted the voltage. So now if you look at this picture and you see that 28.8 microcoulombs of electrons comes out here, it's going to also deposit onto the 4. So this has also a charge of 28.8 microcoulombs. So we could use this again. And we have 4 microfarads right here that accepted 28.8 microcoulombs. What is the delta V, or the voltage? You don't need the delta. Again, you could say voltage 4. Multiply the V to the other side, divide by 4, and you get the voltage here is equal to 7.2 volts. Okay. The next part C and D, were the charge and the voltage right here. How can you find that out? Well, first thing, what I'm going to do is go back to this diagram. This is the easiest thing to do. And I'm going to put a couple points on here. Let's see, how does this color show up? Yeah, pretty good. So I'm going to label this A, and B. And what I'm going to do is find the voltage between those 2 points. And the way I could do that is I know that there's 12 volts here and there's 7.2 here. And I know that this is a series arrangement. So what I could do is I could say that the V total equals V1, or the V4 plus the V6. In other words, I guess I'll have to do here, let's see, so this is going to be, the total is 12 volts. The 4 microfarad we figured out was 7.2, right there. What's this? And we find out that it's 4.8. Actually, let's call this A to B. All right, so that's one part of the process. Now, what do we do with that information? We realize that that point A and point B are here on this diagram. Right? Because it's here to here. Well, this replaced these two. And in fact, we could come back here if we wanted to. And we know that A and B are right here in this diagram. And we know the voltage between here and here is 4.8 volts. The voltage from here to here is 4.8 volts. So we're going to use that now because we now know, if we look at this picture, this capacitor has 4.8 volts on it. Okay? Because it's connected between points A and B. So before I go on, I'm going to have to make a little erasure up there. So let me give you a chance to catch up if you need it. Okay, so let's make some room. Continuing on. Again, I don't want to erase these diagrams. Okay, so actually the D is the voltage from here to here, which we just determined was delta V for the 2 is 4.8 volts. What's the charge? That's part C. Wait a minute. Yeah, we're coming back to C. This is really D. It's getting a little awkward. We're doing C and D together, basically. So now that I know the voltage here to here, I could use that to find the charge here to here by using C equals Q over V for this capacitor. And we have 2 microfarads. We're looking for the charge in that 2 microfarads, and we know that it has 4.8 volts across it. Right there, 4.8. So we multiply the 4.8 to the other side, and we get the charge in capacitor 2 microfarad is 9.6 volts. I mean, microcoulombs. Okay. So let me give you an opportunity to catch up if you need it. Okay, so we learned today that you can connect multiple capacitors together to make a larger, more complicated circuit. The simplest is you can have all the capacitors in series or all of them in parallel. You could have, we did 2 capacitors in series. You could have 3, 4, 100 of them in series. Same thing with parallel. You just keep adding more terms to the formulas that we wrote on the board. So that learn those rules about how charge and voltage and equivalent capacitance are determined in series and parallel. Then we moved on to a more complicated example where we had series and parallel mixed into one circuit. And the way you analyze that is you keep simplifying. You look for a pure series part, replace those. Then you look for another pure series or parallel. It turns out this is pure parallel. calculate their effect, replace them with one. You're always replacing until you get down to your final equivalent capacitance. Then to find the charge and voltage in any piece, you have to go back to your intermediate diagrams and figure out voltages and charges wherever you can, kind of like a little puzzle. And then think about where those points are throughout your diagrams until you solve what you need to. So that's series and parallel circuits and combinations of capacitor circuits. All right, so I'll see you in the next physics video.